So let's continue our discussion of tangent lines and local linearity with the discussion on how to write the equation of a tangent line. So back in Algebra 1, your teachers probably focused on writing tangent line or writing linear equations as y equals mx plus b. But this form is not useful in calculus at all, and Mr. Walker and I beg you not to use it. And the reason why is because it will just create errors and it will make your work more complicated. So what we want to do is use point slope form, which is effectively transformation form, which is right here. So you have some point of tangency, the point x1, y1, and you have a slope. So you want to have x minus x1 and then out here plus y1. We always get the questions, can we use this form, y minus y1 equals m times x minus x1? And of course the answer to that is yes, because they are really the same form. The only difference is that in my form we added y1 to both sides of the equation. So let's practice writing tangent line equations. And we're going to look at the fourth figure on the prior page, which was the absolute value function. And we want to write equations of the tangent lines at the point negative 2, 2, at the point 0, 0, and at the point 3, 3. So the point negative 2, 2, that one we knew that the slope was negative 1 because we were using the left branch of the absolute value function. So to write the equation of the tangent line, we would say y equals negative 1, and then x minus a negative 2, which is x plus 2, and then minus the y value. We're going to go ahead and leave this in the form of point slope form instead of multiplying it out to put it in slope intercept form. At the origin, we did not have a unique tangent line, so we cannot write a tangent line equation where there is not a unique tangent line. And at the point 3, 3, this is where the slope was 1 because we were working on the right branch of the absolute value function. So our tangent line equation is y equals 1 times x minus 3 plus 3. If I were to have asked you to write a tangent line equation for a different figure that was not linear, here's what I would do, and I'm looking specifically at this first figure here. If I wanted to write the equation of the tangent line to the graph at the point negative 2, 2, what I would do is first plug in the x minus a negative 2, which is x plus 2, and then minus x minus a negative 2, and then plus the y value of 2. And I just need a slope here to fit in. Well, what we're going to do is approximate the slope of this line by picking two different points on the line. So let's go ahead and do that together. You can use the point of tangency as one point, and then just pick another point on the tangent line that you sketched that crosses a hash mark if possible. So it looks like the slope here would be rise 2 and then left 1. So the slope is going to be approximately negative 2. You could do the same thing with this point of tangency. You could choose this point and then maybe the point 2, 1 and get a slope that looks like there was a rise of 3.5 and a run to the right of 1. So my slope here would be approximately 3.5, which would enable me to write a tangent line equation of y equals 3.5, x minus the x value of the point of tangency plus the y value of the point of tangency. So now I want you to, it says here to go ahead and take a look back at the figure at the bottom of page 1, which showed an arbitrary function f and its tangent at the point a, f of a. Well, you can flip back and look at that image, but they're asking you to write an equation of the tangent line at that point. So if I'm given a point a, f of a, I'm going to have in parentheses x minus a, and then out here plus f of a. Then we just need to insert the slope of the tangent line, and we've been told that we denote slope as f prime of a. So what we just wrote up here, this is a general equation for the slope of a tangent line at any point on a curve. You will work with this so much that you will have it memorized. It's not a bad idea to memorize it, but this will become second nature to you. So let's just think about a couple of interesting questions. Do you think it is possible for a function to have a vertical tangent line? If so, what would the slope of the curve at the point of tangency have to be? Well, if there were a vertical tangent line, what would the slope of a vertical line be? Well, the slope would have to be undefined, and that line of tangency would have to be in the form x equals. But can that occur for a function? Actually, it can. So here's the example. Look at this function, which is the cube root of x, y equals the cube root of x. This function actually has a vertical tangent line right there at the origin. Here is my tangent line right there. That does not mean that this is not a function. People ask, well, how can you have a vertical tangent line? Because your function would fail the vertical line test if it had 2 points with the same x value. Well, this function does not have 2 points with the same x value. Basically, at the origin right here, the curve goes momentarily and ever so briefly vertical so that the tangent line is vertical, but the function is still a function. So this function has a vertical tangent line at the origin, and the equation of that vertical tangent line, it would have to be in the form x equals, and in this case, it'll be x equals 0. And I've just sketched the tangent line for you. I've just sketched the function and the tangent line for you right here.